Welcome back to ME 760 Engineering Analysis 1. So last lectures we talk about the matrices and how to use the matrices in solving the linear algebraic equation. So we'll continue some of the properties of linear algebraic equation and then move on to the definition of determinants and how we use the determinants to solve the linear algebraic equation. So let's start. So we will define excuse me, a fundamental theorem here for first. It will be for linear algebraic equation, and it is the inhomogeneous equation. So matrix A is multiplied by the vector B is equal to the vector A multiplied by X is equal to the vector B. And also from the Gauss elimination method we define the augmented matrix, which is just matrix, the combination of matrix A and vector B. Whereas of course A is M by N in general and X is N. So for a system of linear algebraic equation AX equal B, there is sets of conditions. The first one is the existence for the solution. So the existence for the solution for AX equal B. In this case, the system of equation AX equal B will have a solution only and only if both A and A augmented, both of them have the same rank. And we defined rank last time as the number of linearly independent vectors or rows, columns or rows in the matrix itself. So if you have, let's say, last time we showed the example that the matrix A has rank of 2 because although it has 3 rows, but 2 of them, if you add them together, it will give you the third one. So the total number of linearly independent rows are 2. And when we flip the matrix and we take the transpose, we transform it to 4 by 3, and we notice that we have 2 rows are linearly independent from the rest of the 4 rows, and the rank of the matrix is still the same. So if the matrix and its augmented matrix have the same rank, so we will have a solution. There is a solution for this problem. And we knew that more specifically for inhomogeneous equation, you either have solution or no solution. And if you have a solution, you might have an infinitely number of solutions or a unique solution. So in order to see whether there is a solution or not, you would check the matrix A and augmented matrix to see if they have the same rank or not. So if they have the same rank, there is a solution. Now, is it a unique solution or not? So this is defined by the uniqueness. For solution, and in this case the rank of the augmented matrix should be equal to the rank of the matrix A, and this should equal to N. So if the ranks of A and A tilde is the same, this means that you have a solution, but in order to have a unique solution, this rank should be equal to for a matrix n by n should be equal to the total number of rows or total number of columns in this case. So if there is infinitely many solution, infinity of solutions, in this case the rank of matrix A should equal to an R, and this R is less than the number of rows or number of columns, and usually we can fix n minus R values of xi arbitrary. And if we check that there is indeed a solution, whether it is unique or infinitely many solution, then we can use the Gaussian elimination or Gauss elimination method can be used to get the solution, to find the solution. So what about the homogeneous system of linear algebraic equations? So now we're talking about the inhomogeneous system. What about the homogeneous system? So the homogeneous system is defined as AX equal to 0. So you do not have the constants here on the right hand of the side of the equation. So if AX is equal to 0, something which is a matrix, you multiply it by a vector equal to 0, there is two possibilities. The first possibility is the vector x is equal to 0, because if you multiply any two things and they are equal to 0, so the vector x might be equal to 0, or if x is not equal to 0, the matrix itself should be equal to 0. So the first possibility that the vector x is equal to 0, this is called the trivial solution. Because all the xi's will equal to 0. And of course, this is not, it is a solution, but this is not the required solution. You can easily say that, okay, if I have a linear system of linear algebraic equation, homogeneous equations, and the system is equal to 0, you can just say, okay, all x are equal to 0. This is not a solution. So if you are, let's say, if you are looking for the temperature distribution at slices, different slices in a cube, you can say that all the temperature are 0, and that's it. But this is not the solution. This is just the trivial solution, and it is a solution. So we will have AX equal to 0 will have non-trivial solution if the rank of A is less than n. So if the rank of A is less than n, we will have the non-trivial solution, and if the matrix A is m by n, if m is less than n, always we will have non-trivial solution. So n is the number of unknown, yes, x1, x2, x3, x4 up to xn, and m is number of equations. So if you have number of equations less than the number of unknowns, always you will have a non-trivial solution, and it will be infinitely many, because you are underrepresentative case. Your number of equations is not enough to solve for the total number of unknowns. So the other theorem that we will be discussing here states that if x naught is the solution for the system AX equal to B, which is inhomogeneous, and HX is the solution for the homogeneous equation AX equal to 0. So this is the homogeneous case. So the theorem states that x equal to x naught plus xh will be a solution for the inhomogeneous equation AX equal to B. And the proof is if x naught is a solution for this, so you can write A x naught equal to B. And if AXH is a solution for AX equal to 0, so AXH is a solution for this equation. So you can add those two equations, so it will give you AX naught plus AXH, and this is equal to B plus 0. So you can take A as a common factor, and this will give you AX naught plus XH is equal to B. B plus the 0 vector, the vector B plus the 0 vector is the same vector B. So in this case, X naught plus H will be a solution for the inhomogeneous equation. It's a very easy derivation. So how we will get the rank of a matrix A, for example? So we said that the total number of linearly independent vectors or columns will give you the rank of the matrix. So usually we will use determinants. So let's move on and define the determinant. So determinants are only defined for square matrices. So if you have non-square matrix, you cannot find the determinant. So for 2 by 2 matrix, the determinant, sometimes we write it D, or determinant of A. If it is A multiplied by B, A, B, C, D. So how we will get the determinant for a 2 by 2 matrix like this? So you take, this is the first element, and you say A, and then you will multiply it by the cofactor here, which is D. Then you take the second one, but usually you give a plus for the first one, minus for the second one, plus for the following, minus for the following, and so on. And if you take the first row as plus, the second row will start with negative, and the third row will start with plus, and the fourth row will start with negative, and so on. So plus minus, plus minus. So A will be multiplied by D. Then you take minus B. If you cross B, the remaining will be C. So it is AD minus BC. So you will start with the diagonal, this diagonal first, and then you will subtract the other diagonal from the first one. This is for a 2 by 2 matrix. What if we have a 3 by 3 matrix? So let's assume that we have D equal to A, B, C, D, E, F, G, H, I. When we get the determinant for a 3 by 3 matrix, it's up to you to solve the determinant either by taking any of the rows or any of the columns. So you can start just by taking the first row and solve the determinant, or the second row or the third row. So if we take the first row, this will be, we'll get the first element, A. We'll cross out the column and row that A will occupy. Then we'll multiply A by the cofactor, the smaller matrix, which is in this case this one. So this is the remaining matrix. So it will be EF HI. Then we'll say minus B. And then if you cross B, the smaller matrix will be DF GI. So this is DF GI. Then the third one, so this is plus minus plus, so it will be plus C. And if you cross C, you will get this minor, and this minor matrix will be DE GH. In the same manner, and instead of just solving for the first row, we can use the second row instead. And if you will use the second row or the first column, for example, if you use the column, so it will be A multiplied by the minor AF EF IJ. Then the second element has a negative here, which is negative D, multiplied by the minor, in this case BC IJ plus H, and the minor is BC EF, and so on.
Should be plus G on the last one.
G? Yeah.
Plus G.
A, B, C, D, E, F, G, H, I. Okay. So, okay. G, and G will be multiplied by B, C, E, F. B, C, E, F. Okay? So what if we have n by n matrix? So we have the determinant in this case would be A11, A12 up to A1n, and AN1, AN2, ANN. So the determinant will be, let's assume that there is AJ1. So the row now will be row number J. So it will be AJ1 multiplied by CJ1. I will define what do we mean by C in a minute here. AJ2, CJ2, AJN multiplied by CGN. This is if you expand along the row number J. So this is expansion along row J. And if you expand along, let's say, a column K, so let's say that this is column K here, and this would be A1K. So this is column K, and this is row number J. So if you expand along any column K, it would be A1K, C1K plus E2K, C2K, up to ANK, CNK, and this is along column K. So what are the Cij? So the Cij's are just -1 to the power of I plus j multiplied by the determinant of Mij, where this Cij is called the cofactor. Cofactors of Aij, and Mij is nothing more than, if you have the matrix here and you have an Aij, so this is column I and row I and column J. So the minor in this case is for this matrix is defined as the minor of Aij. So you cross the column J and the row I, and you will take all the matrix elements that came as a result of crossing this row here. So it's exactly like this one. So if you are solving for E in this case, what will happen? A, B, C, D, E, F, G, H, I. If you are solving for E, you will cross here. And what are the minors now? What are the elements? A, C, G, I. But if you are talking about n by n matrix, you will have a bigger elements in the matrix itself. So the Mij is defined as the minor of Aij. So Cij is the cofactor of Aij, and Mij is defined as the minor of Aij. And it is a matrix n-1 by n-1. Because you eliminate one row and you eliminate one column. So if you have n by n matrix, you will end up with n-1 multiplied by n-1. So what are the properties of the determinant? So we knew now how to solve or how to get the value of a determinant, and we stated that the determinant is only valid for square matrices. So what are the properties? I will give the properties here without proof. So if you interchange two rows or column, this will result in multiplying D by -1. So look at this matrix here for simplicity. A, B, C, D. This is what? AD minus BC. So if you change the rows CD, AB, and this will be CB minus AD. So this is -1 multiplied by the above one, just for simplicity. If you are adding a multiple of row or column to another row to another one, another row or column, this will leave D not changed. if you are multiplying row or column, if you multiply a row or column by C, for example, this will result in the determinant D multiplied by the same value C. Because if you multiply here the row or column here, if you multiply this by C, so A will be multiplied by C and B will be multiplied by C. So C multiplied by A and C multiplied by B, you will take this as a cofactor, and it is the whole determinant is multiplied by C. The determinant of A transpose is the same as the determinant of A, and again the transpose of A, B, C, D is A, B, C, D. Take the determinant for the transpose, it is AD again minus CB. No change. If you have a zero row or column, your determinant is equal to 0, because you can expand the determinant based on the zero row or the zero column, and this will give you 0. So if you look here, let's assume that this is 0. So what's the value now for the determinant? 0. Even if you expand with respect to this one, let's assume that we will expand not with respect to the zero row or column, but we'll expand with this one. So it will be D, and if you make this, so it will be D, and the remaining will be H multiplied by 0 and I multiplied by 0. So this is 0 minus 0. Then this is minus D, and then E will be multiplied by I by 0 and G by 0. So 0 minus 0, and then F, and we'll have H multiplied by 0 and G multiplied by 0. So F will be multiplied by 0 minus 0. So again you will have 0. So if you expand or find the determinant, whether with the column, zero column, or when it was another column, the result is the same, the determinant is equal to 0. So if you have a row or column, that's multiple of another row or column, another one, the determinant also is equal to 0. So again, let's assume that this is AB and this is 3A, 3B. So this would be A minus 3B, A multiplied by 3B, sorry, minus B multiplied by 3A, which is equal to 0. Because now, if you have a row multiplied by a number, it gives you the second row, for example. So those are linearly dependent columns. Linearly dependent column. So finally, the determinant of A multiplied by B is the determinant of B multiplied by A. We knew, we knew from matrices that AB does not equal to BA, but the determinants of AB equal to the determinant of BA equal to the determinant of A multiplied by the determinant of B. So far, do you have any questions? Okay. So what about the rank of determinant? We have a theorem that states that if M by N matrix, A is M by N, and it has a rank R greater than or equal to 1, so the matrix M by N will have a rank R greater than or equal to 1 if this matrix A has an R by R submatrix. R by R submatrix with non-zero determinant, non-zero determinants, and any determinants of R plus 1 by R plus 1 will have a zero determinant. So we'll have a submatrix R by R with non-zero determinant, and every R plus 1 by R plus 1 submatrix has a determinant equal to 0. So if you have something like, let's say, A11, A12, A13, A1n, up to AN1, AN2, AN3, ANN. So if you can find in this square matrix a matrix, let's say, any matrix, let's say R by R, you take R by R, I by R matrix, and you get the determinant of this R by R, and you find that the determinant has a value. So this will be the rank of the matrix. But if you will take R plus 1 multiplied by R plus 1, you will find out that the new determinant is 0. So the minimum dimension that will have a determinant not equal to 0, this will be the rank of the matrix. It's exactly the same when we said the determinant of the rank of the determinant. What we said, it is the what? The maximum number of linearly independent vectors or rows. So we will look for, let's say we have 10 rows or 10 columns. So we'll look for how many of those. I will look for the first row. Then I will look for the second row. Do they have any relation between each other? No. Okay, move on. Third row. No, there is no relation. Move on. Fourth row. Do they have relation? No. Then I reach to, let's say, fifth row or something like this. It has a relation between, it is a combination of the first three, the summation, or something like this. Fifth row? No. Sixth row? No. Seventh row? No. Then at least one of the 10th, it has a linear combination from the 9th. So in this case, the rank will be 9, not 10. So this is exactly the same for determinants. And instead of looking for linearly independent rows or columns, I will look for submatrices. What is the maximum submatrix that has non-zero determinant? So let's say 2 by 2 or 3 by 3 or 4 by 4 or 10 by 10. So if this is n by n, let's assume that I have 10 by 10 matrix that does not have a zero determinant. So this will be the rank. So this is the maximum I can find, not the minimum, the maximum I can find. So this is how you will look for the rank for the matrix. In particular, if you have n by n matrix, it will have an n rank, a rank n, if the determinant is not equal to 0. So if we take the first check to look for the rank for this matrix. This matrix is n by n. So the first check is to do what? Get the determinant. If the determinant is not equal to 0, hey, that's it. This is the rank, n by n. So the rank is n. But if the determinant is equal to 0, then instead of 10 by 10, take 9 by 9. And look for the determinant. Is the determinant equal to 0? Yes. So look for another 9 by 9. All the 9 by 9 combination, let's assume. Then 8 by 8, then 7 by 7. Okay, 10 by 10 is 0, 9 by 9 is 0, 8 by 8 is 0, 7 by 7 is not 0, so the rank is 7 by 7, so rank is 7. Okay? So, if we have AX equal to P, we stated at the very early beginning that AX equal to B if the rank of A is equal to the rank of the augmented A, so there is a solution. Yes? And if the rank of A equal to the rank of augmented A equal to n, in this case if it is n by n, so in this case you will have a unique solution. Yes? So for AX equal to B, it will have a unique solution. It will have a unique solution if the determinant of A is not equal to 0. So if you have A n by n and the determinant is not equal to 0, so this means that you do have a unique solution, only one solution. This is for the inhomogeneous. For the homogeneous one, if AX equal to 0, in order to get a non-trivial solution, non-trivial solution, if the determinant of A in this case is equal to 0. Why? Because if the determinant of A is not equal to 0, X should be equal to 0, so that something multiplied by something is not equal to 0 is equal to 0. Let's say the determinant of A is 3. So you multiply something by 3 and it gives you 0. So X should be equal to what? 0. And this is the trivial solution. So if A, the determinant of A is not 0, this will give you the trivial solution. In order not to get the trivial solution, you have to have the determinant of A is equal to 0, so that X is not equal to 0. Okay? So how we will get the solution for a system of linear algebraic equation? Usually we use the Gaussian elimination or Gauss elimination technique. There's another method to get the xi's or the solution using a method called Cramer rule. And in Cramer rule, if I have the system AX equal to B with the determinant of A is not equal to 0, so in this case I can get the xi's and they will be just the determinants di's over the determinant d. And what's determinant di's? Will be just the determinant of bi's where Bi is just the matrix A with the ith column replaced by B. So let's assume that you have a determinant A11, A12 up to A1n, A21, A22 up to A2n, AN1, AN2 up to ANN, and B1, B2 up to Bn. So the determinant Di will be just A11 up to AN1, and this is the I column, so you will take the ith column here and you replace it by B1 up to Bn, and this is AN1, A1n, ANN. So you will just replace the ith column. So if you need the determinant x1, if you need to get the value of x1, the value of x1 will be the first column replaced by the b's here, so it will be b1, b2 up to bn divided by the determinants of the original matrix A. If you want the x2, it will be the second column, x3, 3 column, xi, it will be the I column. So now we will move to how we will calculate the inverse of a matrix. Inverse of matrix. The inverse of the matrix is defined as A minus 1, and it has the property A multiplied by A minus 1 equal to A minus 1 multiplied by A, and this will give you the identity vector. It's exactly the same like if you say in numbers 3 and 1/3. 1/3 is the inverse of 3. So 3 multiplied by 1/3 will give you what? 1. In matrices, it will give you the identity matrix. So how we will calculate the inverse matrix? The method number 1 is called Gauss-Jordan elimination. Gauss-Jordan elimination. And it is, you will get the matrix A, and now for the augmented matrix for the Gauss elimination, we put what vector here we put? In the augmented matrix, when we solve the augmented matrix? B, yes? And instead of B, we will put the identity matrix. And then you will do exactly the same like the Gaussian elimination. So you will start eliminating and transforming this to the triangular form. In this case, we call it, this is the triangular form, and this is 0 here. And this is another matrix B. So in this case, what we call it here, we call it the echelon reduced row echelon form. And I talked to you about what we mean by reduced row echelon form last time. So you can go and look it. And when you arrive to this situation, this new matrix will be the matrix I, and the matrix B here will be the inverse. So to give you a quick example and move on to the next step, if we have example A equal to 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2, then we will form the AI augmented matrix, and it will be 2 minus 1, 0 minus 1, 2 minus 1, 0 minus 1, 2. Then I will be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, guys? Then you will start do the reduction until you form the following matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. And this will give you 3/4, half, 1/4, half, 1, 1 half, 1/4, half, 3/4. So what you did is, by doing the reduction here, which is the Gauss elimination reduction, until we reach to the form. This is the what? This is the reduced echelon form. And the echelon form, I told you that the leading two things. The leading number here is what? Is 1, and all the leading number in the successive rows are to the right for the leading one. This is the reduced echelon. So this would be what? I, and this would be what? A minus 1. So this is one technique to get the the other one, the second one, is the cofactor method. And this is defined as A minus 1 is equal to 1 over the determinant of A. So you get the determinant of A, and then you get the cofactor matrix. So this is C1, 1, C2, 1, Cn1 up to Cn1, C1, 2, C2, 2, Cn2, and C1n up to Cnn. So what are those?Cij's are the cofactors of Aij's, and the cofactors are given by minus 1 to the power of I plus j multiplied by the determinant, again Aij, and this is n minus 1 multiplied by n minus 1. So to give you a quick example. A quick example is if A equal to minus 1, 1, 2, 3 minus 1, 1, minus 1, 3, 4. First thing, you will get the determinant of A, and the determinant of A, if you get it, you'll notice that it is 10. C11, you will come to C11, the cofactor, so you will eliminate this one, and the cofactor will be this. So when you do, the cofactor will be minus 1 to the power of I is 1, j is 1, multiplied by the determinant of minus 1, 1, 3, 4. And this will give you minus 7. C21, C2, 1, which is this element. So we will cancel this, and this, and this will give you minus 1, 2, plus 1, the determinant, and the determinant will be 1, 2, 3, 4, and this will give you 2, C31, and so on until C33, and this will give you negative 2. Then you will solve for A minus 1, and this will be 1 over the determinant of A multiplied by C11, C21, up to C31, and so on. When you substitute, this will give you the following: negative 7 half over 10, 2 over 10, 3 over 10, negative 13 over 10, negative 2 over 10, 7 over 10, negative 2, over 10, 2 over 10, and 8 over 10. And then that's it. So I will stop here and continue next time because I ran out of time. Do you have any questions? Okay, thank you. See you next time.